Hey guys, my name is Trevor Sullivan and welcome back to my video channel. Thank you so much for joining me for yet another video in our Rust programming tutorial series. The topic that we're going to be covering in this video is a pretty fundamental concept in Rust known as asynchronous programming. Now, most modern day languages have some sort of implementation of asynchronous programming. One of the most notable examples is JavaScript, which is used typically in web browsers, as well as sometimes on the back end to develop APIs. But JavaScript has a concept known as promises, which basically is similar to a standard function implementation, except that it doesn't actually return a value directly. It returns kind of a planned future value that at some point may resolve sometime in the future. Now, asynchronous programming is not necessarily about performance. It gives the aura of performance improvements, but that's only because your program in Rust is able to compute multiple things in concurrency. Now, if you've ever heard the term concurrency, it's not necessarily the same thing as parallel programming. And the reason for that is because when you run a Rust application, by default, unless you explicitly spawn additional threads, you're only going to have a single thread running, which is your main thread. That's the entry point into your application. Now, when we introduce the concept of asynchronous programming, we're not improving the performance of our application at all because we still only have a single thread. You can do multi-threaded programming in conjunction with asynchronous programming, so you can potentially use those models together to improve the performance of your Rust applications, but that's only really applicable if you have multiple CPU cores in a system. As you may know, a single core system is only going to allow a single thread to execute at a given time, so even if you have multiple threads, a CPU is only going to be able to execute one of those threads at a time. And so you're not really gaining any performance on a single core system by running multiple threads. You're just allowing multiple bits of work to be computed kind of simultaneously with each other. So it's really important to understand that using async and await isn't going to give your program any more performance. It simply gives you the perception that your program could be performing a little bit better. To give you one example, just for starters, and I've got kind of a diagram to talk through that shows how asynchronous versus synchronous versus multi-threaded programming works. But just to give you kind of an example to think about in the back of your mind for now, have you ever fired up a graphical interface program, right? Maybe you're building a graphical tool, and when you click on a button, if you have a single threaded application, if you click on a button and you do a bunch of background work, the entire graphical interface can actually hang because when you click on that button and you do the background work, it consumes the only thread that's available for that program. And so what happens is the graphical interface will completely hang while that background work is being done. And then once the background work is done, then the graphical interface or the GUI becomes responsive once again. So that's a great example of where you've got some kind of synchronous process occurring where, hey, this background task is running, and so that's blocking any other kind of work from executing. But by using an asynchronous model, what we can do is basically allow certain processes to kind of pause execution temporarily and politely give control to other types of functions that are attempting to execute within a program. So it gives us this aura of improved experience, and it gives us this aura of kind of having what feels like parallel processing, but in reality, it's not actually parallel processing because you're only ever executing one thread at a time, and only one asynchronous function can actually be executing at one time, even though you can have started execution of many, many async functions at a single time. So we're going to be talking about how the async await works inside of Rust. And for starters, I wanted to kind of talk through a simple diagram here to visually show you the difference between several different types of programming here. So just to give you kind of an overview of this example that I've put together, I have three different customers here. Okay, so we've got three different customers, and each of these customers has a railroad project. And each of these railroad projects has 3 equal units of work. So we have project number 1A, 1B, and 1C. Down here, we've got project 2, A, B, and C, and then project 3, A, B, and C. So we're going to just assume that all of these projects have 3 individual units of work and they're all essentially equal, right? And also, don't worry about distance between each other. So if you have maybe a Eastern US and a Western US railroad, don't worry about travel time in between those different destinations for the worker to actually go work on those projects. We're going to assume that all of these railroads are being built very closely together, and so there's not really any extra travel time involved, right? And then over on the right-hand side here, we have our worker pool. And I just have a single worker here represented by a pickaxe. And that's because we are going to just have our single-threaded application. We're not going to talk about multi-threading when it comes to async await, because that introduces a lot of more complex concepts. And I want to try to keep things simple, especially for anybody who's new to Rust or just new to programming in general. All right, so let's start by talking about a synchronous approach to programming. So at the end of the day, we've got 9 units of work that we need to complete here, right? And we have 3 different stakeholders here, which are our customers, and each of those customers wants to see progress on their railroad project, right? So let's start by talking about a synchronous approach to programming. So in a synchronous approach, if we take a look at a timeline here, this timeline kind of represents the start to finish, where we start working on a project, and the end here represents the completion of all 3 projects, right? So try to think of things from the individual customer perspective here. So customer number 1 right up here is going to be really happy because they are the first project and first customer in the pipeline here. And we dedicate our worker pool down here to this very first project. And so the way that we're basically completing this work is that we start with project part A, and then we go to project part B, and then we complete project part C, right? So this is kind of a synchronous process because we're putting these other 2 projects on hold. And because we only have 1 worker, we can only work on a single unit of a project at a time. So that's why we have to start with part A and then do parts B and C subsequently after part A, right? So only after we complete this entire project can we then move on to the next project, right? So this customer is really happy because their entire project got done from start to finish without any interruptions. Now, the perspective of these 2 other customers may be quite a bit different because these 2 customers have been put completely on hold. Nothing has gotten done on their projects. These projects haven't even gotten started yet because all of our work from this single worker over here was dedicated to this first customer here. So this is a very disproportionate usage of our resources because only a single customer and a single project were worked on during this time period. So now, after project 1 is finished, we're going to move on to project 2. So now our worker is assigned to project number 2. So the worker starts by doing part A of the project, then we do part B of the project, and then we do part C of the project, and everything's great. This customer is now a little bit happier because even though his project was delayed, at least it eventually got completed, right? And once we started on his project, all 3 parts of that project were completed directly from start to finish. So now that leaves customer number 3 here, who's a little bit frustrated because they had to wait for customers number 1 and 2 to be completed. And so then finally, the worker can be freed up to work on project number 3 for the 3rd customer and do projects part A, B, and C in subsequent fashion. So this is synchronous programming in a nutshell because we've only got a single worker that can work on anything. And so basically, to get the work done in the most simplistic fashion, we're just going to start with 1 customer. We're going to finish that entire project and all the parts to that project. Then we're going to move on to customer number 2, do all the parts of that project, and then finally do customer number 3's project, right? So even though this is a functional way to get work done, it doesn't really give a feeling of fairness to all 3 of these customers If all three of these customers came to us at the same time and said, hey, I want to start these projects, then each of those customers is going to have at least a basic expectation that their project is started within a timely manner, right? So this customer number 3 isn't going to want to wait for all of customer 1 and all of customer two's project to get finished before their project at least gets started, right? They want to see at least some level of progress on their project. So that brings us to kind of asynchronous programming. So asynchronous programming is quite a bit different because rather than waiting to start on project 2 for customer number 2 and project 3 for customer number 3, we can actually go ahead and start on customer number 1. So we'll do maybe part A of project number 1 right here for customer number 1. But instead of moving on to do part B of project number 1, we're actually going to kind of context switch and go over to customer number 2 and do part A of customer number 2's project. So now customer number 2 is a lot happier than in the first situation where we did synchronous project completion, because customer number 2's project part A has gotten kicked off and seen to completion, whatever part A is, right? And so customer number 3 is also going to be happy because they didn't have to wait for all of customer 1 and all of customer 2's project parts to be completed before their project was initiated, right? So now all 3 customers, even though we haven't made significant progress on any of these projects, at least all 3 of these customers have the perception from their individual perspectives that their project is being actively worked on and progress is being made on their project. So with asynchronous programming, we have several different chunks of work that are being done more or less in parallel. It feels like it's being done in parallel, but that's only because we are kind of breaking these projects into smaller chunks, and we're focusing on accomplishing a small chunk of that project rather than doing the entire project from start to finish. So we still only have one worker, but we're balancing that worker's allocation across 3 different projects rather than just a single project at a time from start to finish. So with asynchronous programming, we can then cycle back to customer number 1 here. We can go ahead and do part B of project 1, part B of project 2, and project 3 part B as well. Then we'll cycle back once again and maybe do project 1 part C, 2 part C, and 3 part C, and we've still gotten the same 9 units of work completed, but all we did is that we kind of rebalanced the usage of our single worker and allocated it across multiple projects concurrently, rather than necessarily starting a project and seeing that single project through to completion. So this kind of gives you the aura of getting more work done, because from all these 3 customers' perspectives, they're getting a little bit of work done up front, then a little bit more, and then finally a little bit more. So all 3 customers are at least somewhat satisfied with the project progression, rather than certain customers being delayed until the other customers are finished, right? So that's basically what async programming looks like, where we still just have a single worker, but we're able to kind of rebalance that single worker across multiple tasks. All right, so the asynchronous programming is pretty easy to understand, at least at a fundamental level. But then we've got parallel programming, and this is where we've got basically multiple threads, right? So now we've expanded our worker pool from having just a single worker to having 3 workers. So imagine that these 3 workers represent 3 CPU cores, right? So each of these CPU cores can actually be running code at the same time as the others. And in a multi-threaded environment, we're actually able to take all 3 of those workers and dispatch them to different units of work, all at the same time. So we could have this worker right up here be assigned to project number 1. We could have this worker down here be assigned to project 2. And then the third worker could be assigned to project number 3. And so that way, all 3 of these projects can literally in parallel have work being done on them at the same time. And so then once each of these workers is done with part 1 of their project, or part A of their project, they can move on to part B all at the same time. And then finally, they can do project part C across projects number 1 to 3 all at the same time. And so this is really kind of the best of both worlds because we have more capacity to accomplish the same amount of work. And therefore, if you look at the overall timeline, instead of ending way over here, we're actually ending somewhere in the middle because we were able to crunch the entire project timeline down to a smaller period of time because we have more capacity available to us to complete the work. So I want you to kind of use this visualization here to understand how asynchronous versus parallel programming works, because we're not improving the performance of our application. There's no free lunch. I just kind of want you to remember that in your head. There's no free lunch. If you have a single CPU core, you're stuck with a single CPU core. You can't do multiple threads in parallel on that same CPU core. So when we do asynchronous programming, we're not improving the performance. We're simply changing the balance of the resources that we're running in our application. So with that visualization out of the way, let's actually talk about implementation of async and await in Rust. So the way that async works in Rust is that we have this async keyword where we can declare a function as an asynchronous function. So we're basically saying, I want you to do some work. It's kind of in the background, and I want you to return a result to me at some point in the future. So when you use the async declaration on a Rust function, you're actually changing the output type of that function to be what's known as a future, which is similar to, again, a promise in the JavaScript language. So with a future, the future is something that doesn't get executed automatically. We actually have to do something called awaiting that future, and that's where the await keyword comes into play. So once we get a future returned from calling a function, like in this example here, when we call the hello world asynchronous function, we're actually assigning that future to a variable, and then we can call .await on that future, and that's what's going to cause it to actually execute, right? So futures are kind of lazy, that's what we would call them, and until something actually causes them to execute, then nothing's going to actually happen with that future. You can actually execute a function in a program, but if you don't await it, then the future is never going to actually do anything, and your main thread will just exit, and the process will return back to the operating system's control without actually accomplishing any work in that asynchronous function. So in order to execute an asynchronous function, we have to implement something known as an executor. So an executor is basically a mechanism that will drive a future to completion. So it'll take that lazy future and it'll say, I want you to keep doing work until you finally come up with a result. And executors are not available in the default Rust runtime. You can build one yourself by following this article here in the Asynchronous Programming in Rust book, but we're not going to build our own executor. We're actually going to use an off-the-shelf executor. There's several different ones available. There's one from actix, actix. There's one called Smol, smol. And there's another one called Tokio, which is probably the most popular one in the Rust ecosystem because Tokio offers a whole bunch of other kind of file system and network related mechanisms that allow you to do asynchronous file system operations, asynchronous network operations, and things of that nature. So there are several different executors that you can simply install into your dependencies for your Rust project, and then you can use those executors to drive your futures to completion. Now, what does a future actually look like? Well, you can implement your own futures if you want to. So you can either tag your functions as asynchronous, and that'll automatically wrap the return type in a future for you, or you can actually return a custom data type that implements something known as the future trait. And the future trait itself is actually pretty simple. All it does is it declares an output type. So that's going to be the underlying data type that the function eventually returns in the future. That could be any data type like a unsigned 8-bit integer, a signed 16-bit integer. It could be a 32-bit floating point value. It could be a string value. It could be a custom user-defined struct, which we actually talk about in one of my separate videos earlier in this series, defining custom data structures. And as long as that custom data structure implements the future trait, you'll be able to return that from a function, right? So The future trait also is going to declare this type called, or the function, I should say, called poll. So a future needs to implement poll because the poll function is what the executor that we talked about right here, the executor is ultimately just going to continuously call this poll function on the future. And anytime that that poll function is called, that is ultimately what drives forward the progress of the future until eventually that future is completed and a result can be extracted back from that future. That underlying data type that the future returns as its output type here can be then extracted from the future, and your program can then take that value and do whatever it wants to with it at that point. Now, here's the important thing to understand about this poll function. If you choose to implement this poll function yourself, you're going to have to make sure that the poll function returns the poll enum type here. And there's two different variants on the poll enum type. So we've got the ready state, which basically means that the final result is available to be extracted from the future, or we can return a pending state from this poll function. So every time that the poll function is called, it needs to either return pending or it needs to return ready to indicate if it's completed or still pending additional work. Now, in order for the future to make progress, we typically would return pending if we're not ready to return the final result. But then there's another concept here called the waker. So anytime that we call that poll function and we return pending, we also have to wake up the executor and basically indicate to the executor that it's okay to call poll on this future again. And so to do that, we basically implement this type here. It's actually available as part of the context right here. So what we do is we drill into the context and we get this waker from it, and then we can call the wake function on it, and that will allow us to basically wake up the future at some point later on whenever the executor decides to pull it again, and that will allow us to make further progress on a future. If you implement a future and you don't implement the waker to basically wake it back up, then your future is going to basically execute once, it'll pull once, and then it'll indefinitely hang the next time that you try to pull it. So you do need to make sure that you implement the waker function inside of your polling function. Now, I don't want to get too advanced here. We're going to start off with just kind of some of the basics. So how do I define an asynchronous function? How do I implement one of these executors to drive the future to completion? And then we'll get a little bit more advanced into creating a custom future. Now, before we actually get into some hands-on time, I wanted to invite you to support my channel. I'm an independent content creator, so any kind of support that you can lend to the channel is incredibly helpful so that I can bring you more videos like this one. So head over to youtube.com/TrevorSullivan. You can also follow me on x.com, previously known as Twitter, and Facebook as well, using these URLs right here. And if you're on my YouTube channel, please make sure you're subscribed. Please leave a like on the video if you learned something new. And make sure that you check out the entire Rust programming tutorial playlist because I've been adding more and more videos. This will be the 30th video in this series, and there is definitely more to come. So make sure that you just kind of look through the videos in this playlist and see what you like. And then also, please check out the links in the pinned comment down below. Those affiliate links help to support this channel financially so that I can bring you more videos. And leave a comment of your own and let me know what you thought of this video and the others in this video series, because that kind of feedback really helps me to kind of tailor content to the topics that you are interested in. All right, so with that out of the way, let's talk about actually implementing async. So I'm going to go ahead and spin up a new project over here on my Linux server. So let's go ahead and just go into our terminal and we'll do a make dir async-test. And then I'll go ahead and open that up inside of my VS Code editor right here. And then we'll go ahead and just initialize a new binary project by running a cargo init command. And so inside of our source code here, one of the first things that we want to do is to implement an async function. Now, if we try to just put async on our main function here, then you're going to see this error that says that the main function is not allowed to be async. And that's because, as we mentioned just a couple of minutes ago, when you implement a feature, when you return a feature, that feature is considered lazy, right? That feature is not going to do any work on its own until an executor comes in and actually pulls that async feature. So if we make our main function asynchronous, then there's nothing in our program here that's going to drive that feature to completion. So therefore, Rust compiler just kind of indicates that that's an error and won't allow us to do that. But what we can do is make another async function here. So let's do async fn get number, okay? And this function is just going to return something like an unsigned 8-bit integer. Now, as you can see, this is a pretty normal function definition. We have a simple return type here, but the only difference is that we've added the async keyword. So when we add the async keyword, again, that's not necessarily going to return the data type here, a U8. It's actually going to return a future with the output type declared as the return type here. So it's basically wrapped in this future thing, and then that future thing is what we ultimately need to pull in order to push it forward. And again, we're not going to build our own executor. We're just going to use an off-the-shelf executor. But for starters, in order to satisfy the return value here, let's just return a number like 8. Okay, so now up in our main function here, if we call let num equal get number, for example, the Rust compiler is going to infer that the return type here is a future with an output type of U8. So that's that future trait coming into play, which is part of the standard library. And it's basically wrapping the final result that we'll eventually get. But we don't have that until we actually use an executor to execute it. So let's check out the trait itself, the future trait. So this is a really simple definition of a trait here. Again, it just declares this output type and the pull function down here. And this trait can be implemented on your own custom types as well. The easiest way to do this, though, is just to declare your function as async and then declare what your return type is. And the Rust compiler is automatically going to wrap that in a future for you. So you don't have to worry about doing all the boilerplate code to implement the future if you use this syntax here. But there is another syntax that you can use if you want to be a little bit more explicit. So instead of doing an async keyword before the function, you can just declare a regular function, but then you can declare that you want to implement the future type. And in order to do this, we're going to have to say use standard future, and then future. So we want to make sure that we use that trait here. And then what we'll say is that we want to return a future surrounding a U8 type. And then down here, we can actually return a future type that you can go ahead and define yourself. But for now, we're just going to go ahead and do the simple route, which is to use the async type here or the async keyword in order to return this type. That's really just the most simplistic syntax. So now if we try to run this program, we don't have any compiler errors at this point, aside from the warning here indicating that we're not using this variable. So let's satisfy it and just use that variable. And let's turn this into debug output. I'm not sure if future implements debug. Apparently it doesn't. So let's go ahead and actually just comment that out. And then I'll do an attribute here that says allow, and then we'll say unused variables, I think, or unused, what is it? Let's see, warn, yeah, unused variables. So we'll say unused variables, we'll allow that. And we could actually allow that across the entire crate by just declaring it as an inner attribute here. So this will apply to the entire crate rather than just this function or just this line. So now what we can do is to go ahead and run this. So if we do cargo run, you can see that nothing happens, right? And so basically what's happening here is that this future is getting created, but nothing is ever getting done with it, right? We're never actually executing this function. In fact, we can prove that by doing a print line in here, and we could just say running function. And what you're going to see happen here is that I think it is actually going to run the function. But what's happening is that it's not actually getting executed because we're never polling the future, right? We're never using an executor to actually push the future forward and telling it to do some work. So even though we put that print line in there, and technically it looks like we're calling get number right up here on line number 4, we're not ever seeing this result coming back from the function. So the future is kind of wrapping that entire function, and it's not really doing anything because we're not using an executor. So how do we solve for this? Well, this is where the executors themselves comes into play. So we've got a few different executors out there. We've got Smol here. This is one that's available. There's also Tokio. You're going to see this one pop up a lot when you read documentation about asynchronous programming in Rust. And there's also another one called actix here. So actix can actually drive async futures as well. It has its own runtime executor to drive futures, and it also has an actor framework, which is pretty cool. I actually played around with this a little bit a few days ago, and I really like the actor model because it just makes things easy to comprehend, but that is a topic for another day. But there are several different executors out there, and for simplicity, I'm going to use this one here called Smol because this is just a really small crate. Tokio has a lot of other kind of additional features available inside of it, but Smol here is just a really easy one to use. So what we're going to do is actually bring Smol into our project. And unfortunately, yes, if you're going to do async programming, you do need to bring in some dependencies. I know personally, I like to avoid using dependencies if at all possible, but this is one of those cases where we just need to bring in a dependency, or again, you're welcome to look into authoring your own executor. So we'll just do cargo add Smol. And then if we take a look at the documentation for Smol, so we'll go into the crate details here and take a look at docs.rs right here. So one of the functions that is available in Smol is called block on. And block on here takes a future as its input. And this function and the underlying runtime that's kind of backing it is ultimately going to take that async future and it's going to poll it until it's completed. So this will allow us to execute an async function in Rust. So what we're going to do right over here is come into our main function, and after we retrieve the future, we'll say Smol, and then say block on, and then pass in num, which is actually a future, as a function that we want to execute here. So now if we go ahead and do a cargo run right here, now it's going to compile all these dependencies that Smol has along with our program itself. And now our program is actually being executed. Now, the other nice thing about block on here is that it has a generic type T and it returns that back to the caller. And in this case, our future is returning a U8. So let's do let result equal the result from block on here. And because the future that we've created down here returns a U8, as indicated in the metadata right here, then result is simply going to unwrap that value from the finished future, and it'll grab the final value, and then we can use that inside of our main program here. So now we can just say print line, final value is, and then pass in result, and that'll print out the value. So final value is 8, and so that works perfectly fine. So just really remember in your mind that anytime that you return a future, if you're not using a runtime or an executor to invoke that future and pull it to completion, then that future is never going to complete. Now, as I mentioned, you can actually implement your own futures as well. And I think due to the length of this video, I'm actually going to table that topic for a future video. But one of the other things that I wanted to show you is how you can actually kick off multiple futures at the same time. So this example here isn't really giving us any benefit because all we're doing is defining a single function here. We're getting that as a future, and then we're just driving that future to completion. So we're adding a whole bunch of overhead here without really having any benefit, right? But again, going back to the example where we have 3 different projects that we need to complete and only having a single worker rather than having multiple workers, we want to kind of go to that model where we do a little bit of work on this one, a little bit of work on this one, and a little bit of work on this one, right? And in order to really properly demonstrate that, I would actually have to implement my own custom future. But what I can do is define multiple futures. So let's say that we execute this function 3 different times. So now I've got num1, num2, and num3. I'm going to call that num1 just for clarity there. And so now I've got 3 different futures. And what if I want to initiate or kick off all of those futures or all of those projects? Let's say that I want to at least get, step number 1 or project part A done for all 3 of those projects. And I don't want to execute things in a linear fashion where project number 1 has to get completed from start to finish before these other projects can work. So basically, one of these projects is a future, right? We need to get the entire thing done, but we can do it in little bits of chunks, right? So what we're going to do instead of just calling a small block on is we're actually going to bring in this other library called futures. So the futures crate here is going to allow us to have access to a couple of macros. So if we take a look at the documentation for futures right here, and then take a look at macros, you'll see that we have a join macro here, and we also have a select macro. And so these 2 macros are really helpful for basically kicking off multiple futures in, I want to try to avoid using the word parallel, but we can basically use these macros to execute multiple futures, and all those futures can potentially be executing at the same time. Not necessarily processing at the same time, but they're all in progress, I should say, at the same time. Just because they're in progress doesn't mean that they're actively being worked on. So if we use the join mechanism here, basically what we do is we just join, we call the join macro here, and then we pass in references to the futures that we've declared. And then the join macro is only going to return once we have completion on all of those different macros. So what we could do is maybe say, let's do a few different functions here. We'll do async fn num2, and let's just say this returns a u8. But what I'm going to do in this one is return 10. But before we return the value 10 as an unsigned 8-bit integer, we're going to do standard thread sleep, and we're going to sleep for a duration. So we'll say standard time duration from milliseconds, and we're going to pause for 30 milliseconds. And then in our third function down here called num3, we're going to return 12, and we're going to wait for 75 milliseconds. So now we have 3 different functions, and we're going to go ahead and call those. I'm actually going to rename this one to num1 just for consistency here. So now for num1, we'll call num1. For the second one, we'll do num2. And for the third one, we'll do num3. So now we have 3 completely different functions that are asynchronous that we're calling separately. One of them should return basically immediately, and the other 2 have very small pause or sleep periods to them. But if we want to call all of these at the same time, then what we can do is use the join macro by bringing in the futures crate. So let's do cargo add futures. And as long as we bring in the futures crate, we should have access to that macro, and we need to use it right up here. So we'll say use futures, and then we have the join macro right here. Now we can use that join macro and say join, and we'll say num1 and num2 and num3. All right, so let's see what my error is here. So we've got block on, and we're doing a join. And let me just see what's up here. All right, so what I'm missing here is actually that I need to pass in a code block into block on here. So I can't just take join as a macro and return the result from that, because join is actually going to resolve to the underlying values of the futures, and we can't return those directly to the block on function. So what we need to do is turn this into an async block. And so join can be used inside of an async block. So all we're going to do is put our curly braces around this invocation to join, and then we're going to mark that code block as an async block. And so we could go ahead and wrap that in a function separately if we wanted to, but the simplest way to really do this is just to declare an async block and then return the result from the join macro here. Now, I'm going to also eliminate the semicolon there, and that's going to return the final values from this join macro back to the caller here. And now you can see that the Rust compiler is inferring my result as a tuple type with U8, U8, and U8 all inside of it, because num1, num2, and num3 are all futures that eventually return an unsigned 8-bit integer. And then so down here on line number 15, I'm just going to turn this into a debug output because the tuple type can be turned into debug output. It'll just print it just like it looks in code, where it's got the parentheses and the commas separating each of the values. So this join macro needs to be used inside of an async code block here. And so just keep that in mind when you are using it inside of this small block on here. Now, there are other ways to implement executors. So if you're using the Tokio or the actix executors for async, you can actually use those as attributes on main, and those actually allow you to do an async main function. But in the case of Smol here, we don't have access to an attribute. There are some other crates like smol-potat, and they are allegedly attribute-based syntaxes for small async execution, but I did try out smol-potat and it didn't seem to be working the way that I expected it to. So I'm just going to be using smol block on right here inside of a synchronous main function. All right, so let's go ahead and do a cargo run on this project. And as you can see, the final value is our tuple containing 8, 10, and 12. So by using this join macro here, what we're doing is we're basically blocking execution until all 3 of these futures are fully completed and the final values can be resolved from those futures. Now, the other macro that I was talking about is the select macro here. And the select macro is a little bit different because it actually uses a syntax that looks kind of like a match statement. And I've got an earlier video in this Rust series that talks about the match statement in Rust. And what this is going to do is it's going to allow us to examine the different futures, and we can actually respond as soon as one of those futures is done. We can run some code in response to a specific future being completed. So what we can do with this is, instead of doing join in here, what we'll do is use the select macro, and then we use the curly braces here. And I also need to import the select macro here. Since we got rid of join, we can just eliminate that. Or if we want to import both of them, we can use the curly braces with commas to select both of those macros. And so now in this select macro, what we're going to do is declare the different branches that we want to use here. So first of all, we have num1. That's one future that we're going to be dealing with. And so we can do something in response to that, like let's say num1 is completed. And we also need to assign it to a result here. And then the other thing we need to do is do a comma and say num2, and then say print line and say num2 is completed. And then finally, we'll just duplicate that down, make sure that we have commas at the ends of all of these lines as well. And we'll do num3 and set that to the result here. Now, I think I actually need to do unit types as the return values for these, not an underscore. But this is more or less the syntax that we need in order to run these to completion. Now let me see what's going on with these syntax errors here. So it is saying it expects a U8 instead of unit because of course our futures are returning a U8. So what we could do is just assign the result to a variable like x, x, and x. And so then we could use each of those values inside of these print line statements if we wanted to. So we could say, comma x here. Do the same thing for this one. So just print the value that's resolved from each of these in here. And so this will allow us to resolve these futures to their underlying values and then actually use them inside of the select block. Now, the other thing that you're going to notice here is that we are getting this error about a fused future. So if you check out the documentation in the Rust async book, which is right over here, so asynchronous programming in Rust, they actually have a document that talks about the select macro right here. And what you're going to notice is that when you use the select macro, you actually have to call the .fuse function on the future. And what this essentially does is it ensures that when the future is completed, so once it's been pulled all the way to completion, that it's not going to cause any kind of issues when we pull it again or try pulling it again. And because the select statement or the select macro is going to be continuously pulling those futures to see if they're completed, we want to make sure that we have a fused future rather than just a standard future, because we want to avoid having those issues when this is pulled after it's already been completed. So back in our code here, we know that just by looking at the code in these three functions right here, that the num1 function is going to return a value first because it doesn't have any sleep period in it. It's just going to immediately return a value. And so when num1 finishes here, the next time that we pull it, we don't want to cause any errors. So we want to, of course, allow num2 and num3 to continue executing. So what we would typically do is just put this in a loop and say, once all of these are completed, then we can just break out of this loop. But until all of these are finished, we want to make sure that we're periodically pulling them. So the select macro here actually has a couple of special branches. It has a default branch. So let's go down here to the docs. So it has a default branch right here. And the default branch is going to run if let's see right here, if none of the futures are yet complete. So oftentimes, maybe on a first iteration of the select macro loop, it's not going to have any completed futures, so that default branch will be ran. But the next time that the select macro runs and one of those futures does resolve to completion, then that particular branch will be executed. The other important branch that we want to pay attention to is the completion branch. So it's just called complete. And this is where things differ a little bit from the match statement, because match doesn't have complete or default. It just has kind of a catch-all. You can use an underscore to indicate any value in a match statement. But when we use this select macro, we can go and actually break out of the loop construct to indicate that we're finished pulling the futures, and we can now go ahead and just return control back to our program. So we want to make sure that we implement the complete branch here. And then we'll just say print line, all futures have finished, or have, finished polling. And then we'll say breaking out of loop. And then we'll go ahead and call the break statement. And we'll need to put this inside of curly braces because we've got multiple lines going on here. And then the other thing that we just talked about a moment ago is returning fuses. So what we'll do on each of these futures is we'll call .fuse, and that's going to return a fused future instead of a standard future. And in order to use that method, that fuse method, let's check out the documentation for futures over here. And we actually want to find future ext, which is a trait that declares that method. And I think that's actually part of the futures crate, not this one. So let's go to the futures crate. It's not in standard, and we'll do a search for future ext. So here is that trait from futures, future ext. And if we take a look on the left-hand side, sure enough, there is this fuse function that returns a fused future instead of a standard future. And that's what's compatible with the select macro. So we'll say use futures, future, and then future ext, and that will give us access to this fuse function on the future. So now these contain a fuse instead of the future directly, and that will make them compatible with the select macro here. Also, these fuses need to be mutable. So one way to do that is to pin them in memory, which is indicated, I think, over in the documentation here for the book where basically they call, let's see, let's do a search for pin. And I'm not sure which example does that, but they use this pin mute macro here to basically pin them in memory. But we can also just go ahead and do it by making these fuses mutable. So here's the call to the pin mute macro where they're pinning those in memory, but we can go ahead and just do that directly. Now, when I used the mute keyword previously, I was actually using an async main function here. And in this particular case, I'm not using an async main function. So I am going to go ahead and actually remove the mute keyword here from these and use the technique that they have right here. So this macro is available as part of the futures as well. So let's just add pin mute as our import here under our use statement. And then we'll do pin mute and pass in our 3 fuses. We'll do num1, num2, and num3, and that should resolve the scoping issues that we're having with this select macro. So now what we should see, let me fix this one to say num3 here. Now what we should see is that anytime that one of our futures completes inside of this loop right here, it should immediately print out that that future has completed before it indicates that the other ones have finished. So let's test this down here by doing a cargo run. And as you can see right down here, it says num3, num2, and num1 have all completed. And finally, we get the completion branch in that select block, in the select macro, I should say, where all the futures have finished polling. And so then it breaks out of the loop and returns control back to the program. So that's kind of how we can use this select macro to make sure that we are handling all of these different futures and responding to them as soon as they finish, rather than using the join macro where we actually have to wait for all of the futures to finish before we can actually respond to one of them finishing. So in any case, this has been just kind of an introduction to futures in Rust and using async and await in order to pause execution until they're finished and actually resolve a value. And we've also taken a look at some additional features in the futures crate here that allow you to join multiple futures together and pause execution of your program until they're all completed. I would encourage you, if you're doing this on your own, to also take a look at actix, which includes its own attribute that allows you to create an async main function. Also, Tokio allows you to use that attribute-based syntax for an async main function as well. But if you're looking for a lighter weight async runtime, you might want to check out the Smol crate like what we used here. In any case, thanks for watching. Again, please support this channel by subscribing, liking, and commenting, and checking out the affiliate links in the pinned comment below. Thanks for watching, and we'll see you in the next Rust video. Take care.